Here we will discuss some of the numerical problems asked from plasma physics in M.Sc examinations. First section is problems based on P equal to NKT or PV equal to nRT. In P equal to NKT, P is the pressure in Pascal, N is the number density or number of particles per unit volume, K is the Boltzmann's constant, T is the temperature. In PV equal to nRT, P is the pressure, V is the volume, N is the number of moles. So find the difference, because in P equal to NKT, N is the number of particles per unit volume, and PV equal to nRT, N is the number of moles, R is the gas constant, T is the temperature. And there is a relation between gas constant, Avogadro number, and Boltzmann's constant. It is R equal to N0K. The first problem is, given that Boltzmann's constant is 1.38 × 10⁻⁻23, find the number of particles per unit volume. Temperature is 0 degrees Celsius and pressure is 1.013 × 10⁵ Newton per meter square. So it is a direct question. P equal to NKT and N equal to P by KT. Put the value of P in Pascal, K in Joule per Kelvin, and temperature in Kelvin. It is given in degrees Celsius. It is converted into Kelvin. Or we can use PV equal to nRT, but here small n is the number of moles. So the number of particles will be number of moles into Avogadro number, and number of particles per unit volume, it is represented by capital N here. That will be equal to number of particles divided by volume. So that capital N is equal to small n by V into N0, where N0 is the Avogadro number. So N by V is P by RT into N0. Now R equal to N0K. So N0 and N0 gets cancelled, P by KT. We will get the same answer. So here the problem gives the value of Boltzmann's constant, and it is expected to find the result by using only the Boltzmann's constant and the given parameters. Then next problems are based on plasma frequency and maximum penetration depth. Plasma frequency is the oscillation frequency of electrons or the plasma particles. In many cases, if we consider a collection of electrons and ions are almost at rest and electrons are very light particles, so they are considered as the plasma particles. And omega P is equal to Ne square by epsilon 0 m, where N is the number density of the plasma particles, E and M are the charge and mass of the plasma particles, epsilon 0 is the permittivity. And for electrons, this can be written as the plasma frequency in hertz is 9 × √n, where N should be given in per meter cube. And the skin depth is the penetration depth of the plasma particles, of the electromagnetic waves in a plasma. Skin depth is the distance at which the amplitude of the electromagnetic wave depends. It becomes 1 by E times the initial amplitude. It is defined as 1 by K, where K is 2 pi by lambda. It is the wave number in plasma. Lambda is the wavelength inside plasma. And it is given as C by root of omega P square minus omega square, where C is the velocity of light, omega P is the plasma frequency, and omega is the angular frequency of the electromagnetic wave. And in many cases, if the angular frequency of the electromagnetic wave is much less than the plasma frequency, we can write omega P square minus omega square is approximately equal to omega P square, and the skin depth becomes C by omega P. It will be obtained in meter. The first problem is, calculate the plasma frequency and the maximum penetration depth for a plasma density of 10⁻18 electrons per meter cube. So omega P is equal to Ne square by epsilon 0 m. So it is equal to 10⁻18, and E is the charge of electron, epsilon 0, then m is the mass of the electron. So we will get the answer. Or we can find the plasma frequency in hertz by using 9 √n. So it will be 9 × 10⁻9. And the skin depth, it is C by omega P square minus omega square. Here omega, that is the angular frequency of electromagnetic wave, is not given. So we can assume omega as much less than omega p. So it becomes skin depth becomes c by omega p, and it will be equal to velocity of light divided by omega p. It is obtained in the first step. Substituting that values, we will get 0.0053 meter for skin depth. And this is the same question we repeated for in December 2017, but the number density becomes 10 raised to 20 per meter cube, so it can be solved as in the previous step. The answers are given here. And in another question paper, December 2016, it is asked as by using 10 raised to 25 electrons per meter cube. So here also it is solved. It is same step. I am not repeating it once again. Now the next type is the problems based on Debye length and number of particles in Debye sphere. Debye length lambda d is equal to root of epsilon 0 kt by n e square. It is in meter, where n is the number of electrons or ions per unit volume in per meter cube. Remember here, n is the number density of the mobile charged particles in the plasma, that is, whose oscillations are important. Here ions are assumed to be at rest and electrons are moving. But if we take a collection of equally massed positive and negative charges, for example, a collection of electrons and positrons, or a collection of protons and antiprotons, then both of them are to be considered. In that case, n will be equal to the total number density of the charged particles, that is electrons plus positrons or particles plus antiparticles. And E is the charge of one of the particle, C is the Boltzmann's constant, epsilon 0 is the permittivity of free space, T is the temperature in Kelvin. If we substitute the value of epsilon 0, E as taking as the charge of 1 unit, that is 1 electron volt, we get the value as lambda d is equal to, and kt is substituted in electron volt. Then by using another E from that conversion, we will get a result like this, 7430 root of kt by n in meter. For obtaining the result in meter, kt is to be given in electron volt. That is the important point. If you are using this formula, you have to give kt in electron volt and n in per meter cube. Or for electrons, we can use another formula, 69 into root of T by n, putting the value of k, and in this equation, epsilon 0 k by E square. If we put the value for electron, we get 69 into root of T by n, where T is to be substituted in Kelvin and n in meter cube, and we will get lambda d in meter. The number of particles in Debye sphere is volume of the Debye sphere into number density, that is 4 by 3 pi lambda d cube into n, number density. It has no unit, it is just a number. Then the first problem is compute lambda d and nd in a fusion reactor with a capacity of ion concentration from 10 raised to 13 per meter cube to 10 raised to 10 per meter cube, and Te in 0.01 electron volt. So here temperature is given in electron volt range, so it is kte actually, and if lambda d and nd are calculated, we get for n equal to 10 raised to 13 per meter cube. Here in this problem, n varies from 10 raised to 13 to 10 raised to 10, so lambda d and nd also varies between these two limits. For n equal to 10 raised to 13 per meter cube, lambda d is equal to 7430 root of kt by n. Kt is given in electron volt, so we can use this formula. We get the value of lambda d, and corresponding nd is 4 by 3 pi lambda d cube into n. So pi lambda d cube into n is 10 raised to 13, so it will be equal to 543. 542.64, we can approximately take it as 543 as it is a number of particles. Approximation is not necessary, you can stop here also. Then for n equal to 10 raised to 9, Debye length is obtained by using the same formula, but kt is equal to, but this n is equal to 10 raised to 9, and we will get this result. And for number of particles will be equal to 54,264. It is 54,265 almost. And here we can see one point, the lambda d varies from 2.349 10 raised to minus 4 to 2.349 349 to 10 raised to minus 2 meter, and the ND varies from 542.64 to 542.64.7. So as the number density decreases, the number of particles in the Debye sphere increases. That is the important point. It will be proportional to 1 by root n. Then another problem is compute lambda d and nd in the Earth's ionosphere with ion concentration 10 raised to 13 per meter cube and KTE from 0.1 to 0.01 electron volt. So here the problem is similar to the first problem, but here n is fixed and KTE is varying from 0.1 to 0.01. So first to find the value of lambda d and nd for KTE equal to 0.01 electron volt, we will get this result, and then for KTE of 0.01 we get lambda d and nd. So steps are same, only the difference is KTE is 0.1 and here KTE is 0.01 and number density is same, 10 raised to 13. So we get lambda d varies between these two limits and nd varies between these two limits. Here also we can see as temperature increases, we can see as temperature increases, the volume of the Debye sphere increases and the number of particles in the Debye sphere also increases. Then a distant galaxy contains a cloud of protons and antiprotons, each with density n equal to 10 raised to 6 per meter cube and temperature 100 Kelvin. What is the Debye length and the number of particles in the Debye sphere? And there is a B part, find the cyclotron frequency of electrons in a perpendicular magnetic field of strength 3 into 10 raised to minus 4 Tesla. So here the difference is, it contains a collection of protons and antiprotons. Protons have positive charge and antiprotons have negative charge. So here the difference is, in normal plasma electrons and ions are considered, in which ions are assumed to be at rest. But here protons and antiprotons have the same inertia, they have the same mass, so both of them are to be considered. Thus here n is equal to double the number of protons or double the number of antiprotons. They will be same because plasma is Cauchy-neutral. So n is here, n will be equal to 2 into 10 raised to 6 per meter cube. 10 raised to 6 per meter cube is the number density for protons or electrons or antiprotons. So together the n is 2 into 10 raised to 6 per meter cube. So epsilon 0, Debye length lambda is equal to epsilon 0 kt by n e square, epsilon 0, then lambda k is given, then t is given 100 by n is given as 2 into 10 raised to 6. That is the important point. Then e square, because proton have a charge of 1 unit. So we will get Debye length, and then Debye sphere. Number of particles in the Debye sphere, it is also 4 by 3 pi r cube, r is same, that is lambda d. Then n is taken as 2 into 10 raised to 6. So this gives the total number of protons and antiprotons per Debye sphere. So half of them will be protons and half of them will be antiprotons. So there will be nd by 2 number of protons and antiprotons. Each of the proton has this number and antiproton has this number. Then the next problem is omega, that is the angular cyclotron frequency omega equal to qb by m. Q is the charge of the this the cyclotron frequency of electrons. So it is the cyclotron frequency of electrons. So it is the charge of the electron in the magnetic field divided by mass of the electron. So we will get it in radian per second, or the frequency qb by 2 pi m in hertz. Now evaluate Debye length and number of particles in a Debye sphere for Earth's ionosphere with number density of free electrons n equal to 10 raised to 6 per centimeter cube and KTE equal to 0.1 electron volt. So here this is the same question, only the difference is now n is given in per centimeter cube. Before calculation it has to be converted into per meter cube. So 10 raised to 6 becomes 10 raised to 12 per meter cube. Lambda d can be obtained by substituting KT in 0.1. Then END is also obtained, 4 by 3 pi lambda d cube n. Then in a fusion reactor, the core of a small pellet of deuterium and tritium fuels is compressed to a density of 10 raised to 33 per meter cube at a temperature of 5 into 10 raised to 7 Kelvin. Estimate the Debye length and the number of particles in a Debye sphere. So here the fusion reactor contains a pellet of deuterium and tritium. Deuterium and tritium, both of them are ionized. So they have their isotopes of hydrogen. So they are heavy compared to the electrons. So even though deuterium and tritium fuels are there, there will be an equal number of negative electrons. So electrons are more mobile and electrons are behaving for the plasma behavior. We have to consider only the electrons. Deuterium and tritium can be assumed to be at rest. So here we can use the same formula. Lambda d is equal to 69 into root of T by n. T is given in Kelvin and n is given as the 10 raised to 33 per meter cube. It is the number density of deuterium and tritium. It will be equal to the number density of electrons. It is the total number density of deuterium and tritium. So it will be equal to lambda d can be obtained and the nd can also be obtained. Now the next type of problems are based on Larmor radius. The Larmor radius RL is equal to mv perpendicular by qb, where m is the mass of the charged particle orbiting in the magnetic field, b is the strength of the magnetic field in Tesla, q is the charge in Coulomb, and v perpendicular is the perpendicular component of velocity, that is velocity perpendicular to the magnetic field. It will be equal to v sin theta, where theta is the angle between velocity and magnetic field. The first problem is compute the Larmor radius for a solar proton streaming with a velocity of 240 km per second perpendicular to a magnetic field of 5 × 10 raised to minus 5 Tesla. What is its value? Means what is the Larmor radius for a 1.1 kilo electron volt helium plus ion with the same in the same field. So for proton it is R is equal to mv by qb. So here mass of the proton into velocity, it is given as 240 km per second. So it will be 240 × 10 raised to 3 meter per second divided by charge of the proton into magnetic field. So it will be 50.1 meter. And for the case of helium ion, we are provided with the kinetic energy of the ion. Velocity is not given, and kinetic energy of the ion is 1.1 kilo electron volt. It is much less than the rest energy of helium ion. So we can use the non-relativistic result for the kinetic energy. So it is half mv square is equal to ke. Therefore v is equal to 2 into k root of 2 ke by m, that is root of 2 into kinetic energy is 1.1 kilo electron volt. So it will be 1.1 into 10 raised to 3 electron volt. Then now it will be converted into joule. So 1.1 into 10 raised to 3 into 1.6 into 10 raised to minus 19 divided by mass of the helium ion is, helium ion contains 2 protons and 2 neutrons in the nucleus. So mass will be 4 into 10, 1.67 into 10 raised to minus 27. We will get the answer as velocity of the helium ion, and therefore radius, Larmor radius is mv by qb. So mass is 4 into 1.67 into 10 raised to minus 27 for helium ion into velocity divided by charge. It is helium ion is He plus, so it is singly ionized, charge is same as the electron, and 5 into 10 raised to minus 5 magnetic field. We will get 191.2 meter. The next problems are based on the Lorentz force law. The force on a charged particle moving in a combined electric and magnetic field is F is equal to Q into E plus V cross B, where F is the force on the particle. It is not mass, it is the force of particle in Newton. Q is the charge of particle in Coulomb, E is the electric field in Newton per Coulomb, and B is the magnetic field in Tesla, and V is the velocity of particle in magnetic field. Remember, this F is not the mass, it is the force acting on the particle. First problem is a magnetic field B equal to I plus 2j minus 4k exists in a certain region of space. If a test charge is moving with a velocity of v equal to v0 3i minus j plus 2k, it experiences no force at a certain point, then find the electric field at that point. The total force F is equal to Q into E plus V cross B. It is given as 0 because experiences no force. It means that E plus V cross B equal to 0. It means that E equal to minus V cross B or equal to B cross V. So E equal to B cross V, it is equal to IJK. Then the coefficient of B are 1, 2, minus 4, and the coefficient of V are 3 V0 minus V0 then 2v0. We will get the answer as E equal to I into 2 into 2 4 v0 minus 4 into minus v0, so plus v0, so minus 4 v0 minus j into 2 v0 plus 12 v0 plus k into minus v0 minus 6 v0. So we get the electric field as minus v0 into 14j plus 7k. A hydrogen nucleus passes along a straight line through a region with a uniform electric field of 6 Newton per coulomb and a perpendicular uniform magnetic field of 8 into 10 raised to minus 5 Tesla. The particle moves perpendicular to both the E and B. Calculate the velocity of alpha particle. Here the electric force and magnetic force are equal and opposite, so we can use QE equal to Q into V cross B, that is QVB, because particle is moving perpendicular to both the E and B. So velocity V is equal to E by B. 6 by 8 into 10 raised to minus 5, so 7.5 into 10 raised to 4 meter per second. And the next are problems based on cyclotron frequency. Cyclotron frequency omega equal to QB by M, or in radian per second, or in hertz it is QB by 2 pi m. Q is the charge of the particle, B is the magnetic field, and M is the mass of the particle. Important point is cyclotron frequency is independent of the radius of the orbit or velocity. It depends only on the charge and mass of the particle. Find the cyclotron frequency of electrons moving with a speed of 100 km per second, making an angle of 45 degree with a magnetic field of strength 3 into 10 raised to minus 4 Tesla. This is a direct question. Omega equal to QB by M, and there is an extra two quantities are given, that is 100 km per second velocity and making an angle of 45 degree. They are not required for finding the cyclotron radius, because cyclotron radius depends only on the charge, mass and magnetic field. So it will be given in radian per second, or by using F is equal to QB by 2 pi m in hertz. Here Q is the charge of the electron and M is the mass of the electron, and B is the given as magnetic field. Find the cyclotron frequency of alpha particles moving with a speed of 300 km per second, making an angle of 60 degree with a magnetic field of strength 6 to 10 raised to minus 4 Tesla. Here also QB by 2 pi m. Q is the charge of the alpha particle, it is 2 into 1.6 into 10 raised to minus 19. And M is the mass of the alpha particle, it is 4 into 1.67 into 10 raised to minus 27. B is the magnetic field. We will get the cyclotron frequency in radian per second or in hertz. Now other problems are, it is in plasma physics, it is usual to give the temperature in units of energy as kT. So there is a simple problem. In plasma physics, it is customary to give temperatures in units of energy. Calculate the temperature corresponding to an energy of 1.5 electron volt. Boltzmann's constant is given. Here kT can be approximately taken as 1.5 electron volt. So kT is equal to 1.5 electron volt. So that is equal to 1.5 into 1.6 into 10 raised to minus 19 joule. It is 1.5. That will be T is equal to 1.5 into, that is kT is converted into joule divided by the Boltzmann's constant. We will get it is 17,391.3 Kelvin. So these are the various problems asked for M.Sc examination. You can prepare, and wish you all the best.